This is section 2.3, Systems of Linear Equations. In this section, we're going to talk about what a system of linear equations looks like, how to verify a solution to it, how to solve it using three methods, the graphical, substitution, and elimination method, and finally we'll look at some applied problems to systems of equations. Let's start with the definition of a system of equations. A system of equations is a set of equations with common variables. All of the systems that we'll be looking at in this lesson will be linear systems, meaning our equations will represent lines, and the variables that we'll often be using are x and y because we see those often when we graph our lines. The solution that we're looking for to a system of equations is an ordered pair, so a point, and we're looking for the a and the b values that represent the x and y that result in our equations having true statements. So what this all boils down to is we're looking for an ordered pair or a point that both equations have in common. That intersection point is the solution to the system. So that's what we'll be looking at graphically in our first method. We're going to solve using the graphical method, or solve a system by graphing. Again, we're looking for a point they have in common or an intersection. So we're looking for two different ways that our equation can be written to begin with. The first one is slope-intercept form that we've talked about before. So a quick review of that. If we want to graph slope-intercept form, the first thing we do is graph our y-intercept, which is our b. And the second thing we do is from that y-intercept, we use our slope, which is our m. And remember, when we graph that, it's a rise over run, is how we move from the y-intercept to get another point on our line. The second equation is what we called standard form. And the best thing to do if you're given an equation in standard form is to get the y alone, so isolate it. And then from there, when your y is alone, you'll have slope-intercept form, so you can graph using the slope and y-intercept. All right, so here's our first example of a system of equations. So again, we have two equations that represent lines for us, and they have variables in common, an x and a y. What we're going to do is graph both of these equations. Starting with the first one, notice my y is alone, so I can name my y-intercept 3, and my slope, the number in front of my x, -2. And we're going to think of that as a -2 over 1 when we do our rise over run. From there, I'm going to make a point at 3 on my y-intercept, my y-axis. And then because my slope is -2, from that y-intercept, I'm going to go down 2 and right 1. Down 2 and right 1. Remember, you always run to the right. You either rise or fall, depending on if you have a positive or a negative slope. You could even go the other direction a little bit if you wanted to, using that same slope. So there is our first line. Let's look at the second one. Again, we have slope-intercept form, so I can name my y-intercept 5 and my slope 3. Again, I'm going to think of it as a 3 over 1. To graph, I'm going to make a point at 5 on my y-axis, and then I'm going to rise 3, run 1. Do that a couple times. And there is my second line. What we're looking for in a system, remember, is the point that they have in common, or the set of x and y values that work in both equations. So you can see that somewhere close to the y-axis in this example. If I had to approximate it, I might say something around -0.5 and maybe 3.5. Again, that's just an approximation. Graphing in most cases is not a very accurate method, but it's nice to see the visual, which is why we always start with this method. If you want to get an exact answer using the graphical method, you use your graphing calculator. So let me bring my calculator up here. Okay. So the first thing that we're going to do is we're going to go to y equals, and we're going to clear out any equations that are in there. You also want to make sure your plot is off. You can see my plot at the top is off there. and we're just going to type our two equations in. My first equation is y equals negative 2x plus 3, and my second equation is 3x plus 5. To graph, you can just graph on your default window, so you might not be in your default window. You might want to hit zoom 6 to get to that default window. If you were already there, you could just hit graph, and you can see those lines match the lines that we had a moment ago. To find the intersection, we're going to go to a menu that we've used a few times already, second, trace, which is our calculate menu. And remember, we used the zero method. We've done mins and maxes in here before. To find the intersection, we're going to choose number 5, intersect. Okay, we've done that before with our solving equations. We graphed both equations and found the intersection. All you have to do here is hit enter, enter, enter. Once you've chosen intersect, and the little blinking cursor will show up at the intersection point, and at the bottom of your screen it would tell you what the intersection is. So very close to what I estimated here. The exact answer is negative 0.4 and 3.8. Okay, let's look at another one of these. These two equations are not in slope-intercept form, so we have a little work at the beginning to get them in that form. Let's start with the top equation. I want to get the y alone, so let me rewrite the equation here. 6x minus y equals 8. To get the y alone, to get it in slope-intercept form, I'm going to subtract 6x on each side. So now I have negative y equals 8 minus 6x. And then from there, I'm going to divide everything by negative 1 to get the y alone. That gives me y equals negative 8 plus 6x. So my b, my y-intercept, the number by itself, is negative 8. And my m, my slope, is 6, the number in front of the x. I'm going to think of that as a 6 over 1. When I graph it, I'm going to make a point at 8 on my y-axis. I'm going to rise 6 and run 1. Up 6, 3, 4, 5, 6 over 1. And there is our first line. Let's do the second equation. My second equation is negative 3x plus 2y equals 2. To get the y alone, I'm going to add 3x on each side. 2y equals 2 plus 3x. And then from there, divide everything by 2. Y equals 2 divided by 2 gives me 1 plus 3 halves x. So my b, my y-intercept is 1, and my m, my slope, is 3 halves. I'm going to make a point at 1 on my y-axis to start, and then my slope is 3 over 2, which tells me to rise 3 and run 2. And there is my second line. In this problem, you'll notice we actually plotted the same point twice in both of our equations. So we can say pretty confidently that 2, 4 is the point of intersection and the solution to this system. If you want to check this answer without your calculator, which by the way, you could check it with your calculator, you could plug these into your calculator where the y's alone and use that intersect method. But you can check the point in the original equations. I'm going to plug 2 in for my x's and 4 in for my y's. That's going to look like 6 times 2 minus 4 equals 8. Well, 6 times 2 is 12, minus 4 gives me 8. 8 equals 8 is a true statement, and that tells me that this point works in the first equation. It's important when you're checking a solution in a system that you check it in both equations, because it's possible that a point can work in one equation but not both. So let's plug 2 in for our x and 4 in for our y in the bottom equation. That's negative 6 plus 8, and that gives me 2 equals 2, which again, it checks. So that's how we algebraically check a solution works in a system. Okay, try this graphing problem on your own. Okay, to graph this, I'm going to get the y alone in the top equation, which will give me y equals 2 minus x. You have to subtract x on each side. That tells me my b, the number that's by itself, is 2. Slope, the number in front of my x, is negative 1. I'm going to think of it as a negative 1 over 1. Make a point at 2 on my y-axis. From there, I'm going to go down 1, right 1 a few times. And there is our first line. When you're drawing these, you want to keep that line as straight as possible. You can use a ruler, a straight edge, whatever works for you. In the second one, I'm going to subtract 4x on each side. So I'll have y equals negative 1 minus 4x. My b, my y-intercept, is negative 1. My m, my slope, is negative 4. So from here, I'm going to make a point at negative 1 on my y-axis. Because my slope is negative 4 over 1, that tells me to go down 4, right 1. And I might have to go the other direction here to get my intersection. There we go. There's my second line. And you can see that I have the same point on both of my lines, and that point is negative 1, 3. Is the solution to your system. If you want to check it, negative 1 goes in for x in both equations, 3 goes in for y in both equations, and you should get 2 true statements. All right, let's look at the 3 different things that can happen when you're solving a system of equations. Case number 1 is you have 2 lines that intersect, like the last 3 problems we just saw. We say that that system has one solution, which is the point of intersection, and we call that system unique. So you might see that word pop up in your MyMathLab. The second case is if we have parallel lines. So remember what we know about parallel lines. We know they have the same slope, and they have different y-intercepts. Parallel lines also never intersect, which means if we're solving a system and looking for a point of intersection and they don't have one, we then have no solution. This type of system is called inconsistent. Again, a word that might pop up in your MyMathLab. Finally, the third case is if our lines are the exact same line. So this line looks kind of purplish because it's the blue and pink lines from above actually on top of each other. It's telling us line 1 and line 2 are the same. If 2 points are always intersecting, that means any point on the line, and there are an infinite number of points on the line, is a solution to the system. So we say that if they're the same line, we have infinitely many solutions, and we call the system dependent. You'll know when you're solving algebraically, so not by graphing, by hand, if you have one of these 2 special cases, the parallel case or the same line case, if when you're solving all of your variables drop out and you're left with 2 numbers that are equal to each other. If all of your variables drop out and you're left with 2 numbers that are not equal, like 2 and 3, we know those are not equal. So we say that that is a false statement, and that would tell you that you have parallel lines and no solution. If when you're solving, your variables drop out and you're left with a true statement, like 5 equals 5, that tells you that this set of equations is always true, meaning they're the same line, and therefore you have infinitely many solutions. So you want to look for these as you're solving in the next 2 cases that we discuss. If all of your variables cancel, it's one of the special cases. If it's false, it's no solution. If it's true, it's infinitely many solutions. Let's look at our next method. Our next method for solving is the substitution method. And let me fix my formatting here a little bit for you. There we go. All right, so solving using substitution. We're going to walk through one problem here as we discuss each step so you can see what it looks like. So the first step in substitution is to isolate one variable, which means get one variable alone in one of the equations. So let's look at the problem on the bottom. The variables that don't have anything in front of them, no negatives, no numbers, are the x in the top equation and the y in the bottom equation. So either of those would be good choices here. I'm going to get the x alone in the top equation. To do that, I have to add y on both sides. So this equation becomes x equals, the y's cancel, 5 plus y. That's all you do in step 1. Step 2 says take what that variable is equal to. So when we see that x is equal to 5 plus y, we're saying they're the same thing. X is the same thing as 5 plus y. And plug it into the other equation. So if x is the same thing as 5 plus y, I can plug 5 plus y in for x. I can replace it in the other equation. Make sure you use parentheses when you substitute. So I'm going to take the x out and replace it with what it's equal to, 5 plus y equals 7. From there, I'm going to distribute my 2. Actually, hold on. Let me go back here. That's actually the end of step 2. Step 3 now, you should have one equation with all of the same variables. So I have one equation with all y's, which means I can solve this equation. So again, I'm going to distribute the 2 in. 10 plus 2y plus y equals 7. Then running through our steps to solving, the next thing I can do is add my y's together, add my like terms. So I have 10 plus 3y equals 7. Then I can subtract 10 on each side. That would give me 3y equals negative 3. And then I can divide both sides by 3, which would give me y equals negative 1. That's step 3. Once you get one answer, either your x or your y, in step 4, you're going to plug that back into one of the original equations to get the second half of the point you're looking for. You can use either original equation. I'm going to use the bottom equation. 2 times x plus, now we know what y is. Y is negative 1. And now we can solve for x. If I add 1 to the other side, I get 2x equals 8. Divide both sides by 2, I get x equals 4. So my final solution as a coordinate, as an ordered pair, is the point 4, negative 1, which again, in step 5 now, if you wanted to, you could plug that back in as we've practiced with the graphing problems. Plug 4 in for your x's, negative 1 in for your y's, and make sure it works for both of your original equations. Let's do another one together here. Again, we're still solving using substitution. So the first step is we want to get one of my variables alone. The only variable that doesn't have anything too messy in front of it is this y in the top equation. So let's try to get that alone. The first thing I'm going to do is I'm going to subtract 4x to the other side. So I will have, I don't want to write it that way. I take that back. There we go. I'm going to have negative y equals 4 minus 4x. And then I still have one more step to get the y alone. I'm going to divide everything by negative 1. So now I have y equals negative 4 plus 4x. That's the end of my first step. In the second step, I'm going to substitute what that y is equal to in for y in the second equation. So that looks like 6x plus 3, make sure you use parentheses, negative 4 plus 4x equals 15. That's the end of step 2. Step 3 is solve that equation. So let's distribute our 3 through. That'll give me a negative 12 plus 12x. Then I'm going to combine like terms. I have 6x and 12x. That gives me 18x. There we go. We got it working. Okay. Sorry about that. 18x minus 12 equals 15. I'm going to add 12 to the other side. So I have 18x equals 27. And then divide both sides by 18. I'm going to get x equals 27 over 18. Both of those numbers are divisible by 9. So we're going to say x is 3 over 2. That's step 3. Step 4, plug that answer into either original equation. I'm going to again use the bottom equation. 6 times 3 halves plus 3y equals 15. Think of that like a 6 over 1. If I multiply those together, I'm going to get 18 over 2, which is 9, plus 3y equals 15. Subtract 9, 3y equals 6, y equals 2. So my final answer here is 3/2, 2. And then if you want to check it, again, you can plug that back in and make sure it works in both original equations. Here are 2 problems for you to try. Just like the other problems, you do have a choice at the beginning about what variable to get alone. So I'm going to tell you right now which variable I would get alone. That way when you check your answers in a few minutes, your work will follow along with mine. But if you want to try it a different way, you're welcome to do that as well. In the first equation, I'm going to get the x in the top alone. In the second system, there's no variable here that doesn't have anything in front of it. So I'm going to get the y on the bottom alone because every number I see there, every coefficient is an even number. And if I divide by the 2 in front, at least I won't have any fractions. Okay, try these 2 on your own. All right, so in problem number 1, if you get that x alone, you should have x equals 1 plus 3y because you added 3y to the other side. Step 2, circle what it's equal to and plug it in for that variable in the other equation. So then you have negative 2 times 1 plus 3y in parentheses plus 6y equals 3. Distribute my negative 2 in. I'll have negative 2 minus 6y plus 6y equals 3. And then when I add together my like terms, I have a negative 6y and a positive 6y. They actually cancel. So I'm left with negative 2 equals 3. So this is what I talked about earlier. When you have all your variables cancel and you're left with either a true or a false statement, you have a special case. In this case, negative 2 does not equal 3. We have a false statement. So we say that this has no solution. This also tells you that the original equations are parallel lines, so you could graph it to see those parallel lines, and we would also call this system inconsistent. Again, a word that may pop up in your My Math lab. Let's look at number 2. For problem number 2, I want to get the y alone in the bottom equation. To get that y alone, I'm going to subtract 4x on both sides first. So that would leave me with negative 2y equals 6 minus 4x. And then I'm going to divide everything by negative 2. Now I have y equals negative 3 plus 2x. And I'm going to plug that in for y in the top equation. That top equation now will look like 3x plus 4 times negative 3 plus 2x equals 10. And the first step to solving this is we distribute. So I'll have a minus 12 plus 8x. Combine like terms, 3x and 8x give me 11x. Then I'm going to add 12 to both sides, so 11x equals 22. And then divide both sides by 11. I'm going to get x equals 2. From there, I want to plug that back into either original equation. Let's say I use the top equation, sounds good. Again, either one would work. 3 times 2 plus 4y equals 10. That's 6 plus 4y equals 10. Subtract 6 on both sides, 4y equals 4, and I get y is 1. So your final solution here should be the coordinate 2, 1. All right, let's fix the formatting for this one on here a little bit. And then we're going to talk about the third and final method to solving a system. This one is called the elimination method, and it is my personal favorite. All right, and again, we'll walk through this example on the bottom as we discuss the steps so you can see what each of these look like. In the first step, we're going to adjust the coefficients by multiplying through a number so that the coefficients of the same variable are opposite. What this means is we want in one of our equations to have a variable term, let's say it's 3x, And then in the other equation, we want the opposite variable term, so a negative 3x. Or maybe we have a negative 4y and a positive 4y. One pair of variables needs to be opposite. And in your equations, if they aren't already, you want to make sure everything's lined up nicely for this method as well. It doesn't say that here, and in this example, we won't have to line anything up, but we'll see a problem a little bit later on where we want to make sure everything is lined up and ready to go. So in this bottom equation, I need to decide what to multiply by to get opposite variables. So one thing I could do is I could multiply the top equation by negative 3. That would give me a negative 9x. The bottom is a 9x, and those would be opposite. Another option is I could multiply the top equation by 2. If I multiply the top equation by 2, I would have a 4y and a negative 4y, and I would have opposite y variables. So either one would be a correct method to solve. Notice also everything's lined up in this problem. Most of the time we like this standard form where the x's and y's are on one side and the constants are on the other. I'm going to choose to multiply the top by 2 here because I don't like multiplying through a negative. Sometimes it's easy to make a mistake with that. So if I multiply 2 through the whole equation, and I put my equation in parentheses so I don't forget anything, I would get 6x plus 4y equals 6. And that's all we do in the first step. The second step is add the equations together. And the reason we want these opposite variables is when I add my equations together, one of your variables should drop out. 6x and 9x give me 15x. This is also a great reason why they're all lined up because we're adding down columns here. 4y and negative 4y cancel. 6 and 4 give me 10. And that's all you have to do for step 2. Step 3, you should have a really simple equation now, and we can solve for x. I'm going to divide both sides by 15, and I'll get x equals 10 15ths, which both of those are divisible by 5, so I'm going to get 2/3, and that's all you have to do for step 3. Step 4 now is the same step we used with substitution. Once you get one answer, you're going to plug that back into one of the original equations and solve for the other variable. So let's say I use that top equation. 3 times x is 2/3 plus 2y equals 3. From there, I'm going to multiply 3 times 2/3. That would just give me 2 because my 3's cancel. Plus 2y equals 3. Subtract 2. I get 2y equals 1. And then divide both sides by 2. I get y as a half. So my final answer here is 2/3, 1/2. And again, the fifth and optional step here is if you want to check it, it's the same way we check every other method. Plug those answers in for x and y in the original equations, and if you get two true statements, that is your solution. Let's do another one of these together. And oh, my formatting is not working out today. For some reason, the word of is not being loved by my program. All right. So again, I've got the steps up here for you. Notice these equations at the bottom are not lined up. So let's do a little work before we do any of those steps. In the top equation, I want my x's and my y's on the same side, so I'm going to move this 2y over to the left. That would make that equation look like 3x minus 2y equals 1. In the bottom equation, I don't want that 1 with my x and y. I want to move it to the other side. So I would have to add 1 on both sides. That would look like negative 7x plus 3y equals 1. All right, now let's go through our steps. The next thing I need to do is adjust the coefficients so I have opposite variables. You'll notice it's going to be difficult to multiply 3 by something to make it look like 7 or 2 by something to make it look like a 3 without having to use fractions and decimals. So this is an example where we're going to multiply both equations by a number. So let's put my parentheses here. If you're not sure what to multiply by, the easiest thing to do is to pick two numbers that are in front of the same variable and switch them. So I'm going to multiply the top by 3 and the bottom by 2. That would give me a negative 6y and a positive 6y. If I had the same sign, I could also multiply through a negative, but the y's are already opposite, one positive, one negative, so I'm good to go there. Let's distribute those numbers in. 3 through the top gives me 9x minus 6y equals 3. 2 through the bottom gives me negative 14x plus 6y equals 2. I'm going to add my equations together. negative 5x. My y's cancel, one's positive, one's negative, equals positive 5. And actually I've done step 1 and step 2. I multiplied through, I added my equations, and now to solve this I'm just going to divide both sides by negative 5. And that gives me x equals negative 1. From there you can plug that back into either original equation. I'm going to use the top one. If I use the top equation, it's 3 times x, so 3 times negative 1, equals 1 plus 2y. So that's negative 3 equals 1 plus 2y. If I subtract 1 on both sides, I get negative 4 equals 2y, and then divide both sides by 2, y equals negative 2. My final answer is negative 1, negative 2, and if I wanted to check it, I would plug this in for x and this in for y in both equations and make sure I get 2 true statements. Okay, I want you to try these on your own. Again, there's lots of different ways to do these problems, so I'll show you what I'm going to multiply by as a first step here. In step number 1, or excuse me, system number 1, I'm going to have to multiply both equations by something to get opposite variables, and because my y's are already opposite, one positive, one negative, I'm just going to switch those numbers. I'm going to multiply the top by 2 and the bottom by 5. That switching method will always work with elimination, so if you're not sure what to multiply by, that's kind of our fallback. Take two numbers that are in front of the same variable and switch them, and just make sure one's positive, one's negative. In the second system, I have a 4 and an 8. I can multiply the top by 2. That would give me a positive 8, and that will eventually cancel out my negative 8. Okay, so there's a hint for your first step. Go ahead and try these on your own. Okay, in system number 1, if I multiply the top by 2, I have 8x minus 10y equals negative 34. If I multiply the bottom by 5, I have 15x plus 10y equals negative 35. Add my equations together. I'll get a 23x. My y's cancel, equals negative 69. And then divide both sides by 23. That's going to give me x equals negative 3. From there, you can plug that back into either original equation. I'm going to use the bottom equation, but if you use the top, you'll get the same answer. 3 times my x, negative 3, plus 2y equals negative 7. Negative 9 plus 2y equals negative 7. Add 9 on both sides. 2y equals 2, y equals 1. And there's my solution. My solution is negative 3, positive 1. Let's look at problem number 2. I'm going to multiply a 2 through the top equation. 8x minus 6y equals 18, and then I want to add them together. 8x's cancel. Oh, and actually here my 6y's cancel also. If everything cancels on one side, you have nothing left, so we put a 0. 18 and negative 18 also give me 0. So all of my variables canceled. I have two numbers equal to each other. In this case, it is a true statement, so we say that there are infinitely many solutions. This means, remember, that these are the same line, so you could check that by graphing, and we also call this a dependent system. If you see that word pop up on MyMathLab, that's what that means. All right, the last thing we're going to do in this lesson is we're going to look at a couple application real-life situations where you would use linear systems. The first example is about college enrollment. Suppose the percent of males enrolled in college within 12 months of high school graduation is given by the following equation. So y is the percent, and we have negative 0.126x plus 55.72. And then females also have a similar type of equation. Again, the percent of females, y, within 12 months of college that are enrolled, or 12 months of high school that are enrolled in college is 0.73x plus 39.7. It also tells us that x is the number of years after 1960. So for example, if my x was 8, that would be the year 1968. or if my x was 40, that would be the year 2000. Use graphical methods, so it's telling us we want to solve this by graphing, to find the year. These models indicate the percent of females equaled the percent of males. So we're trying to find the year, x, where the y, the percent, are equal. So in other words, we're trying to find an x and a y that are the same that work in both equations, aka an intersection or a system of equations solution. Again, we're supposed to use this using graphical methods. You could graph this by hand, but I would definitely say this is a good one for the calculator because of the decimals. So in your calculator, we're going to go back to y equals. We're going to clear out the equations that are in there, and we're going to put in the first equation, negative 0.126x plus 55.72. My second equation for the females is 0.73x plus 39.7. And if you hit graph in your standard window, you should see what I see, which is absolutely nothing. So remember that x and y here represent years since 1960. And right now we're seeing negative 10 to 10, which doesn't really make a whole lot of sense, doesn't give us a wide range. And y is a percent, and we're only again saying negative 10 to 10. So let's change our window here a little bit. Again, x represents years since 1960. So let's say 0 through, well, right now it's 2020. That's 60 years after 1960. So let's make our x minimum 0, because again, it doesn't make sense for negatives in this problem. And we'll make our x max 60, which will take us up to at least this year. X scale, you can change this if you want. That's how often you see a tick mark on your graph. So let's make it 10. We'll count by 10s on our x-axis. Y's, again, are our percentage. The only things that make sense are percentages from 0 to 100. So that's what I'm going to make my y's, 0 to 100. And again, I'm going to count by 10. So now, if you hit graph, we're going to be able to see those lines, and we're going to be able to see that intersection point. As soon as you can see the intersection point, we're going to do the same method we did before. Second, trace. We're going to choose intersect, number 5, and then hit enter 3 times. Enter, enter, enter. So let's see what we got here. We have an intersection at 18.7 and 53.36. So what does that represent? 18.7 is about 19. So it's about 19 years after 1969. So that means approximately 1979. Again, 19 years after 1960. And what does our y represent? Our y represents a percentage. So in 1979, there were about 53.36% of males and females enrolled in college 12 months after high school graduation. Okay, let's look at another application problem. This one has to do with market equilibrium. The demand for a brand of clock radio is given by the following equations. Let's write that down actually. Demand equation is P plus 2Q equals 320. And the supply equation is given by P minus 8Q equals 20. It tells us what our variables represent. P is the price and Q is the number of clocks. We want to solve the system containing these two equations to find the price that demands when the demand and supplies will be equal, and then the equilibrium quantity, which is a fancy way of saying the quantity, again, when these will be equal. So again, we want the price when they're equal, we want the quantity when they're equal, so we're looking for when these equations are the same or the intersection point. You can solve using any method you like here. It didn't specify. If it's me, I'm going to solve using elimination because that's my favorite, and everything's lined up here nicely. You could also use substitution in this problem. I'm going to multiply the top equation by -4. Actually, not -4, just a +4 would work here. That would give me an 8Q and a -8Q, and I could get my Q's to cancel. So the top by 4 will give me a 4P, 8Q, and 1,280. Add my equations together. I'm going to get a 5p, my q's cancel, equal 1,300. And then you can divide 1,300 by 5, and that's going to be p equals 260. From there, you can plug that back into either original equation. I'm going to use the top equation. So p is 260 plus 2q equals 320. Subtract 260 on each side. So I'll have 60, and then divide both sides by 2. Q equals 30. So that's the set of values that make these equations equal, which, what does that represent in real life here? P is the price, so I guess we're assuming $260. It's an expensive clock radio. Maybe it's $2.60. Maybe it's price in pennies. $260 is the price for 30 radios, was the quantity that make the supply equal to the demand. So it causes equilibrium in this situation. All right, the last two slides, we're just going to practice writing a system of linear equations, which then if you want extra practice, you can go ahead and solve these as well. But typically, if you're not given the equations, this is one of the more difficult things to do with systems. So we just want a little extra practice with this. The first problem has to do with stock prices. It says the sum of the high and low prices of a share of stock in John's Inc. in 2012 is $83.50, and the difference between these two prices in 2012 is $21.88. Find the high and low prices. When you're creating a system of linear equations, you are going to have two variables, and you're going to have two equations that both have those variables. So the first thing you want to figure out is, what are our variables? What are we solving for? Well, it said to find the high and low prices. So those are our two variables. You can use whatever letters you want to represent these. If it's me, I'm going to try to use letters that are easily relatable to what I'm solving for. So H for high and L for low. That way when I solve for H, I know immediately it represents the high price, versus if I use an X and a Y, I would then have to go back and figure out what that represented. All right, so now that we have our two variables that represent high and low prices, let's write two equations that each have an H and an L in them. The first piece of information I was given is the sum of the high and the low prices is $83.50. Well, sum is a fancy way of saying add. So that says we add H and L together, we get $83.50. The difference, which is a fancy way of saying subtract, between the two prices is $21.88. And it must be high minus low, because if it was low minus high, we would get a negative number. And that's your system. And that's where we're going to stop on this problem. But when you do the homework, then you'll have to solve it using one of the methods that we've talked about. For this problem, if you want to try it on your own, I would suggest solving using elimination, because everything's lined up and your L's are actually already opposite. So you could add the equations together to get those L's to cancel. Let's look at the second one. In the second one, this has to do with pricing of concert tickets. A concert promoter needs to make $84,000 from the sale of 2,400 tickets. The promoter charges $30 for some tickets and $45 for others. So what we don't know here, what we're solving for, is how many of each type of ticket the concert promoter is going to sell. We know the lower price ticket is $30 and the higher price ticket is $45. So again, we could use an L and an H here. L for the low price and H for the high price. The first piece of information we're given is that he wants to make $84,000. That's a total. So that's going to go on the right side of my equation. So this will be our dollar equation, is what this is going to represent. And how he's going to make that $84,000 is he's going to sell L tickets at the $30 price, and he's going to sell H tickets at the $45 price. Add those together, and that's going to give him his income, his $84,000. The other total you're given in this problem is 2,400 tickets. So we're going to write a ticket equation. We're going to work backwards from that total. We know that he sells L of some and H of another. So total, that L and H must add together to be 2,400. Now what we don't know is it 2,400 or 1,200 and 1,200? That's what you have to solve for. But we do know that the number of tickets he sells at the low price plus the number of tickets he sells at the high price are going to give you 2,400 total. This problem you could solve using substitution if you wanted to try it on your own by getting the L and the H, one of those alone in the bottom equation. Or you could solve using elimination by maybe multiplying by -30 on the bottom, and that would get your L's to cancel. So again, you can try that on your own if you want that practice. In the next problem, we're going to look at an investment situation. We just got these last two here. A woman invests $52,000 in two different mutual funds, one that averages 10% per year and another that averages 14% a year. If her average annual return on the two mutual funds is $5,720, how much did she invest in each fund? And again, that last sentence there is telling us what we're solving for. How much she put in each fund. And there were two funds, one that was 10% a year and one that was 14% a year. So maybe I'll use T for the 10% fund and F for the 14% fund. All right, and again, we have two totals, so we're going to use those, like the last problem, to work backwards. We have an investment amount, that's a total, and then a return, which is a fancy way of saying interest earned on the accounts. All right, so the 52,000 is split between two funds. So whatever she puts in the 10% fund plus the amount she puts in the 14% fund must be 52,000 total. So again, we don't know what it is. It could be 26 and 26,000 or 20 and 32,000. That's what we'll solve for. The second equation is the interest equation. So this is where we're going to actually use the interest rates. 10%, so as a decimal, move that decimal 2 spaces to the left, 0.10 goes into T dollars goes into the 10% fund. Then I have F dollars that go into the 14% fund. So as a decimal again, 0.14. And that gives us total 5,720 will be the interest earned. So there's your system. If you don't want the decimals in this problem, one optional step is you could multiply the bottom equation by 100. That would move all the decimals 2 spaces to the right and give you whole numbers. You could also solve this problem using substitution by getting one of the variables in the top equation alone, or by using elimination. Maybe multiply the top equation by, I don't know, -0.1, and then you'd have a -0.1t and a +0.1t, and you could get those to cancel. All right, the last problem we're going to look at is about medication. A nurse has two solutions that contain different concentrations of a certain medication. One of them is a 30% concentration and the other is a 15% concentration. How many cubic centimeters, cc's, of each should she mix to obtain 45 cc's of a 20% solution? So again, we are mixing two things together. How much of each is what we're trying to find. So 30% solution, I'll just use an X for that. And 15% solution, I'll use a Y to represent that. Again, you have two totals, so we're going to work backwards. I know total cc's need to be 45, and I know the final percent needs to be 20%, which is 0.20, so we'll call that our percent equation. So the first equation, I need 45 cc's. What we're trying to figure out is how many cc's of each concentration. And again, we don't know how it's split, but we know that the two solutions, X and Y, we're going to have a little of one, a little of the other. Total, that's going to be 45. So we add those together. The second equation is now, again, where we're going to use the percentages like we did with the investment problem. 30% solution, and we're going to use X cc's of that solution. We're going to use Y cc's of the 15% solution. Now we're not actually quite done here. You'll notice in the last problem we had those percentages. What we were we got at the end that 5720 was already the total with the interest calculated in. What we have at the bottom here, this percentage, it's just a percentage. It has to be a percentage of something. So when we say of in math, we mean multiply. And let's talk about what needs to go there. 30% of X cc's in that concentration. 15% Y cc's in that concentration will give me 20% of the total cc's. And we know the total cc's is 45. So this problem's a little tricky because you actually use that 45 twice. Again, if you want to solve, this problem would be good for either substitution or elimination. You could also, as an optional step, multiply the bottom equation by 100 to get rid of the